Okay, moving on, we're going to talk about slope fields a little bit. And we'll talk about what is a slope field, how to build them, and what do they tell you about solutions to differential equations. So a slope field is a graphical tool, displays dy dt, the slope, at each point in the plane, and it gives you a little tangent line. And you may have seen this sort of thing in calculus. Solution curves to the differential equation have to be tangent to the little tangent lines in the slope field. So what does that look like? So we'll sketch the slope field for this. And notice this is just a calculus problem because there's no y's on the right-hand side. So we'll start by setting up a little table, t dy dt. When t equals 0, if we plug that into here, what do you get? You get 1. When t equals 1, if you plug t equals 1 into here, you get 1 plus 1 in the bottom, so 1/2. And likewise, if you plug in minus 1, you get 1/2. If you plug in 2, you get 1 plus 4 in the bottom, so that's 1/5. Plug in minus 2, you get 1/5 as well. So what does that tell us about slopes? Well, this vertical line, this is my y-axis, this is my t-axis. This vertical line is t equals 0. And all along the vertical line t equals 0, I want dy dt to be 1. So whatever my slope, whatever my solution curve is, it's got to go through the y-axis with a slope of 1. And so a slope of 1 is about 45 degrees. And so I can just draw in a bunch of little line segments of slope. 1. So whatever my solution curve is, it's got to be tangent to one of those things when it goes through the y-axis. Now at t equals 1, it's got to have slope 1/2. So not quite so steep. And we're just drawing a bunch of these things, kind of get a little Bob Ross here going with a lot of happy little slope 1/2. And then at t equals 2, we want slope of 1/5. So that's even shallower. It's a little hard to tell the difference. Boop, 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 boop. And then t equals -1. We get these slopes of 1/2 again. So there should be some kind of a slope, but not as steep as slope of 1. And then out at t equals -2, a whole column of happy little slopes close to being horizontal. Right, and you can fill them in, and you can tell that as we go from t equals 0 to t equals 1, the slopes in this gap here are going to go from being a slope of 1 to a slope of 1/2. They'll get less steep as we go through there. So what does a solution curve look like? Well, if you pick a place to start, that is your starting condition, the solution curve that goes through that starting condition has to be tangent to that line. And as it goes off to the right, it has to be increasing because all your tangents are positive, but not increasing quite so fast, concave down. And then it has to be tangent to that when it gets there, and when it gets out here, it has to be tangent to that, and it keeps getting flatter and flatter and flatter as you go out to the right. As you go out to the left, right, it's still, the function is still increasing because the derivatives are positive, but it's increasing more slowly. So it has to be tangent there. Then when we get out to t equals -2, it has to be even more flat. And so your solutions look like that. If I could draw better. What happens if we start at this point? Well, that's got to be the tangent line to the curve. And then the curve has to continue off to the right and increase in steepness till it gets to here. And then it increases in steepness till it gets up to there. And then decreases in steepness, decreases in steepness. It sort of flattens out to the left and it'll flatten out to the right. So you can draw in the various solution curves. And the thing is imagine the plane covered with little tangent lines of the appropriate slope. And then you draw curves that are tangent to that. So we have dy dt equals 1/1 plus t squared. Separate the variables. Then we can integrate both sides, and that gives us y equals arctangent or inverse tangent of t plus c, because the derivative of arctangent is 1/1 plus t squared. Great, and so this is the graph of arctangent. right? That's my solution curves. What does the plus c do? Well, adding a constant just moves the graphs up and down, right? Our slopes are independent of y, so you can move them up and down, right? There's no y here, so you can move them all up and down as much as you want, and you'll keep the same curve, same shape, right? Because along each vertical line, all the slopes are the same. And so you can draw out your solutions. And you may have seen this sort of thing in calculus. So here's a different equation. Here, we've got a y and a t in our solution. So what does the slope field look like? Well, here, instead of saying that we just have t, we're going to actually have to look at points, t comma y. And then what's the slope at that point? So the sort of obvious ones to start with are with 0 and 1. What are our slopes? Well, dy dt is y plus t, so 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1. These two have the same slope. Minus 1 plus 1 is minus 1. 0 plus minus 1 is minus 1. And so we can start graphing our slope field. At the origin, we have slope 0, so we draw a little horizontal line there at the point 1, 0. This is my t-axis, this is my y-axis. 1, 0 is here. We've got a slope of 1. T equals 0, y equals 1. That's up on the y-axis with a slope of 1. T equals minus 1, y equals 0. It's here. We've got a slope of minus 1, so slope it down. And same thing here. We've got a slope of minus 1. So, interesting. So these two things have the same slope. So in fact, whenever t plus y adds up to 1, right, you're going to have a slope of 1. So suppose we have the point minus 1, 2. What's the slope at that point going to be? It's going to be, well, 2 plus minus 1 is 1. And minus 1, 2 is up here. And so we have a slope of 1 there. So in fact, along the line, y plus t equals 1, your slope is equal to 1, right? Because that's what this is. And that's the line y equals 1 minus t. And that's this line. And everywhere along here, you have a slope of 1. And that makes these, when you can find these sort of symmetries, that makes these, drawing these things out a lot easier. Okay. So the line y plus t equals 0, that will give you a slope of 0. And that's y equals minus t. So that's this line here is y equals minus t, goes through the origin. And all along here, you have horizontal slope. If you look at the line y plus t equals minus 1, right? What's the slope along that line going to be? Well, it's going to be minus 1. And the equation of that line is minus 1 minus t. And that's, in fact, this line here. And we'll get a bunch of, it's a slope minus 1 there. And one more, if you have y plus t equals minus 2, you'll have slopes of minus 2. And that's the equation minus 2 minus t. And that would be a line out here. And here my solution, my slopes are minus 2, which are steep negative slopes. And as we go out this way, right, my y plus t just gets bigger and bigger as I go out that way. So we're going to have steep positive slopes out here. And if I go out this way, y plus t is just going to get more and more negative, and I'll have steep negative slopes there. So what do my solutions look like? Well, if I start at the origin, going forward in time, we start out with a horizontal tangent, and then we have to have slope of 1, and just get steeper and steeper and steeper. Going backward in time, well, in the gap here, slopes go from -1 to 0. And so they're negative slopes like that. And so we're going to have to work our way backwards like that. If I start at this point, going forward, I'll just have steep negative slopes. Going backwards, my slopes will be negative, but shallower. And they'll work the way back like this. And then if I actually start on this line, right, y equals -1 minus t, well, that line is in fact tangent to all of those the line itself is tangent to all the slope curves. The line itself is tangent to all the little tangent lines, right? So our actual solution here is y equals -1 minus t. And that is an actual solution. We can actually check that. dy dt equals -1, right? That's checking the left-hand side, y plus t, and y plus t equals -1. So this is actually a solution. If we take this function and we plug it into this equation. So, what can we say about solutions? How do they relate to the value of y0? So if you start below this line, well, let's actually do this. Start above y equals -1 minus t, right? All of your solution curves will look like that. So your solution curves look like this. On y equals -1 minus t, your solution curve is just that line. And if you start below it, your solution curves look like that. And they're actually asymptotic to this line in backwards time. So drawing these things is messy. Luckily, GeoGebra can do a lot of this for us. So we'll go and look at GeoGebra real quick. Where is my GeoGebra? There it is. So there's GeoGebra. And we will start calculator. And fortunately for us, GeoGebra has a slope field command. And we'll just put in x plus y. And remember, where I use a t, they use an x. So there's the slope field. You can see sort of the same thing we've got before, right? And right down, nope, want to do that. But if you look right along in here, there's a place where the slopes are all -1. And so we can actually add some solutions to this. So suppose we take solve ODE, and our right side of our equation is x plus y. And the point, suppose we start at -1, 0. That should be a comma, because otherwise it goes a huge fit. There it is. So -x -1, we saw that. That's our solution. And it's tangent to all the little slope field lines along there. And we can choose other starting positions. Keep doing that. Solve ODE, hit enter. X plus y is our vector, is our right side of our differential equation. Suppose we want to start at the origin. So what's the solution that goes through the origin look like? So we'll put in 0, 0. And it looks like that, right? The orange curve here. And so as we go from the origin back in time, it's becomes asymptotic to the green line, and forward time it goes up to that. And then finally, suppose we start somewhere below Oh, solve down, enter x plus y, and so suppose we'll start at -2, 0. Right, so there's our initial condition is right there, and our gray curve here is the solution that goes through -2, 0, that's here, and it is in forward time, just getting steeper and steeper going away. So you see there's two types of behavior that most solutions have, either the orange one or the gray one, and then there's a dividing line, the green line, which separates those two types of solutions. And GeoGebra can do these sorts of things. It can generate slope fields for you, it can generate solution curves, and you can sort of see how solution curves should look. And it also gives you actual equations. So -x minus 1, that's the green curve. -x minus 1 plus e to the x, that gives you the orange curve. -x minus 1, which is the green curve, minus e squared e to the x, that's the gray curve. So it'll actually give you the formulas for the solution there as well. So we'll go back to the lecture notes. There we go. So we checked our examples. Oh, you can go back and check this one for the solutions to the arctangent problem. So what we know, we'll talk about existence uniqueness later. What we know is that when you have a slope field, the solution curves never cross, right? And so what we found in our slope field example from 2 was that we had this nice straight line solution. And in the slope field, when you draw them, the solution curves never cross. So if I start up here, what that tells me is that I can never, a solution that starts up here can never cross this line and end up down in this part. And in fact, we saw that any kind of solution curve looks something like that. Likewise, if I start down here, any solution curve that starts down here can't cross this straight line solution. And so it has to remain on that side of that line. And now that we have this solution, of course, right, this solution, if I pick a point out here, the solution that goes through this point can't go through this solution either, right? So they have to be sort of nested in a particular way. Great. And so that gives us a start on slope fields.